Okay, so in today's lecture, we will be trying to understand the analysis and design of pile cap, which we also know as pile supported foundation. Basically, this is the pile cap. You can clearly see in this figure. It rests on the piles and it supports the pier or column above it. Okay, so basically, the load is coming from the pier or column and going down to these piles through this pile cap. And in this video we will try to learn the design of this pile cap. Okay, this is the statement, the problem statement, basically, that based on a geotechnical study, a pile supported foundation is required to support a heavily loaded building column. So this is not a bridge system, this is a building column. That's why it is calling a column. Okay, building column. If we were talking about the bridge, then it would have been pier. Understand it? Okay, further it says that design the pile cap shown in the figure on next slide with the 12-inch diameter piles. Okay, the piles underneath it will be 12-inch in dia and a service load capacity of 50 tons each, and each pile will be able to carry 50 tons load. The pile cap has normal weight concrete, number one, with a compressive strength of 4000 psi, number two, and steel will be grade 60, number three. The piles are embedded 4-inch into the pile cap. Okay, so the piles will be embedded 4-inch into the pile cap. The axial loads on the column are due to dead and live loads and are equal to 425 kips dead load and 250 kips live load. Okay, the following hand solution will be used for a comparison with the finite element analysis and design results of the engineering software program. Okay, so I will show you the hand solution, and then there will be a comparison with finite element method solution. This is basically the layout of a reinforced concrete pile cap. See, this is the column, the building column, which is resting on the pile cap, and then pile cap is lying on these piles. So this is the elevation, and this is the plan. You can see the column, the rectangular one, this one column. Okay, two piles are right at the middle of the pile cap, and three each at sides of the column, sorry, the pile cap. Okay, three at this side. If we term it as north south, so three piles are at the north end and three at the south side or south end. This is the description of the contents. We saw the we will see first the dimensions. Then in the second phase will be the pile cap shear strength and thickness, one way shear at column, one way shear, sorry, two way shear at the column, one way shear at the column. Then two way shear at corner pile, one way shear at corner pile. Then two way shear at interior piles. Okay, pile cap overall depth requirements. So these will be the checks that we will discuss for the shear. Then for the flexure, pile cap flexural strength and reinforcement, factored movements, required flexural reinforcement, then reinforcement bar development length, and finally we will compare the results with the finite element solution. Okay, this is the design data. We already saw this in this statement, and these are the dimensions. You can clearly see from this figure. Okay, the plant dimensions of a pile cap depend on the number of piles. Number one, that how many piles are you providing that are needed to support the load. Okay, number and arrangement of piles were determined from unfactored forces and moments transmitted to piles and permissible pile capacity selected through geotechnical engineering principles. So at this point, these things are already determined. These calculations are not part of the scope of this example. See, as I told you, pile spacing is generally a function of pile type and capacity, whether it is a friction pile, it is an end bearing pile, or it is a combination of both. The following figure shows the piles configuration selected by the reference for this example with the associated pile cap plan dimensions. Okay, so you can see the dimensions of the pile cap. Let's first discuss it. This is a 7 feet 9 inch by 8 feet and 6 inches. Okay, so these are the dimensions of the pile cap. You know the dimensions of the piles. These are 12-inch in diameter. uh, Talking about the transverse direction from the center of the pile to this end is 1 feet 3 inches, that will be 15 inches. The distance between the consecutive two layers of piles is 2 feet and 7.5 inch. See both these distances. And in the longitudinal direction, the end distance is same. See, however, the distance between two consecutive piles, center to center distance is 3 feet in this direction. Okay, the size of the column is 1 feet 10 inch. It's a square column, and the distance between center of the column to the center of piles is 1 feet 6 inches, and the center line of this column is also the center line of these piles. Okay, so this is the geometry and the plan dimensions of this pile cap along with the column and the piles. With the approximate plant dimensions determined based on a suitable number of piles for the applied design loads, the determination of foundation thickness can be completed by examining shear and flexure strength at critical sections. So we know the dimensions, we are just left with the depth of the foundation or thickness. The pile configuration selected in the reference is intended to illustrate the implementation of code provisions in ACI 13425 pertaining to the calculation of factored shear based on pile location with respect to critical shear section. Okay, so now coming for the critical shear. The thickness of the pile cap is initially determined based on the following key parameters. Number one is two-way shear requirements around the column. See column which is at on the above, okay, and the top side of the pile cap. One-way shear requirements at the column, and one-way and two-way shear requirements around the piles, both the corner piles and the interior piles, and pile cap overall depth minimum requirements. So these four requirements need to be fulfilled. It says both one and two-way shear are investigated at the critical sections around the vertical elements, for example columns, supported by the pile cap with the requirements of ACI 1342. Factored loads are used to compute the shear forces at the critical sections around columns as well as piles, as we discussed here. Like footings, it is common practice not to use shear reinforcement in pile caps. One-way shear checks are shown for illustration, as two-way shear normally governs the design. The overall depth of pile cap shall also be selected such that the effective depth of bottom reinforcement is at least 12 inches. Okay, so these points need to be observed while designing the pile cap depth. Number one, two-way shear at the column. The total factored axial load on the column Pu is equal to 1.2 dead into 1.6 live. You know the values for the dead and live. So putting the values, it gives you a total of 910 kips of factored load. Consider a uniform distribution of column load to the provided piles. Because of the rigidity of the pile cap, this assumption will be verified later using a finite element method. Okay, so there are total of 8 piles. You can see from the figure. See 3 plus 3 6 plus 2 8. So dividing the factored load by the number of piles, we will get 114 kips load on each pile. Okay, assume this is acceptable given pile capacity given in the reference. Assuming that the center of the two piles closest to the column are located at 6 inches or more inside the perimeter of the critical section for the two-way shear, so their contribution to the total shear can then be neglected. And it says that this assumption will be verified later. Okay, so these two piles, this one and this one, it says that it is within the 6 inches of critical shear perimeter of this column. Therefore, we are ignoring these two piles and it will be verified later. Therefore, the factored shear force at the critical section is calculated based on 6 of the 8 piles only. Okay, so we are ignoring the 2 piles at the middle. So VU will be equal to, we know the capacity of each pile 114 multiplied by 6, so we have 684 kips. The design shear strength for the interior column is by this equation, which is given by ACI. Putting the values, we will get the result of, uh, if we put pi is equal to 0.75, we will get the result for depth requirement. The minimum required D for the pile cap foundation can be calculated by setting the VU equal to 5 VC. Okay, so from this equation we will get the value of depth equals to 21 inches. By using D is equal to 21 inches, the center of two piles closest to the column is located at 3.5 inches inside the critical section, which is less than 6 inches. Okay, see this figure. Okay, we will come to this figure. Thus, the initial assumption is not valid. That is, part of the reactions from these two piles must be considered in the shear force at the critical section. Or number one solution is that the assumption is not valid. If you want to keep this assumption valid, then a bigger D must be selected. So the current D is 21 inches. It says if you increase D to 26 inches, then the center of the piles is located at dp by 2 inside the critical section. And these reactions can be neglected and the assumption made earlier is validated. These configuration changes are for illustration only for the students and may not represent optimal design. Okay, it is up to the design professional based on project criteria that whether he is going with this increasing in depth or he is going to make another assumption. So this was the first point when D was 21 inches, and this is the second one when D is 26 inches. Okay, so when D is 21 inches, so the critical perimeter is 43 inches. We know the size of the column, which is 22 inches. This one is 43 minus 22, 21 divided by 2. Okay, so this distance is 21 divided by 2, which is equal to 10.5 inches. Now the uh, the center to center distance between the piles and the column is 18 inches. So uh, uh, we are left with 3.5 inches. Okay, now this distance is 3.5 inches and this is less than or equal to die of pile divided by 2, which is 6 inches. So in this case, you cannot ignore the reaction of the piles and its contribution in the shear capacity. However, if you increase the depth up to 26 inches, so your critical parameter is now increased. The one side is 48 inches. You can clearly see that by after deducting the values, you are left with 6 inch difference between the center of the pile and the uh, critical shear parameter. So the design shear strength for the interior column, we are talking about the interior column, we are putting the values. See, you know all the values. 5 VC is equal to 947, which is much greater than 684 kip. So okay, thus two-way shear requirement around the column is uh, satisfied. Please note that you have not used the exterior column equation here. Okay, now one-way shear at the column. We talked about the two-way shear, right? Now we will be discussing about one-way shear and in north-south direction. See, this is the north-south direction. The critical section for one-way shear is located at a distance d from the face of the column. It is at the distance d from this face. See, we are talking about the north-south direction. So this is the either you have to go to the north direction or to the south side. So we are talking about the north side. This is the face of the column and the depth is 26 inches. So going about to 26 inches, we are at a distance of 5.5 inches from the center of these piles. The center of the three piles is located 5.5 inches, as I showed you from, in the figure, which is less than dp by 2. Okay, dp by 2 is 6 inches, as you can see here. So in this case, the pile reaction shall be based on a linear interpolation between full value at dp by 2 outside the section and zero value at dp by 2 inside the section. So it's a simple linear interpolation that either the line is lying outside at for example at 6 inches, and the second assumption is line is lying at this point at the center of the piles. So in this case a contribution will be like it says 0, okay, and in other case you have to take the full value if it lies outside. So using the linear interpolation values for both the assumptions, this is for zero caves when it is inside the pile center line, and when it is outside you have to consider the full value or full reactions. By performing interpolation with the center of the three piles is located at 26 minus 5.5, which is 20.5 inches from the face of the column. So the reaction from each pile is equal to total reaction 114, which is a full reaction, into 20.5, which is your current distance or location of the D from the face of the support, divided by 32 minus 20. What is 32? The full distance. And what is 20? Where the distance when it was at center line of the piles, minus 1.667. And what is this 1.667? Okay, so the factor load or the load carried by each pile into the value at which we are interested. For example, the pile center, just like here, the center of three piles is at 20.5 divided by the upper limit minus lower limit. Uh, uh, the term you will get it minus 1.667. This is the offset distance between the this line and your line of critical parameter. So it turn comes out to be 5 kips. Therefore vu is equal to 3 into 5, because there are three piles in a row, 1 2 3, and you are doing for these three piles. 3 into 5 is equal to 15 kips. This is your vu. Now checking the shear capacity, so putting the values in this equation, it comes out to be 252 kips. So vu is 15 and this is 252. So one way shear is not a case okay to be considered, but we just applied the checks. So 5 vc is much more greater than vu. Okay, the same is the case in the east west direction. The previous one was in north south direction, right? So this was the line. Now east west direction, so you will see the critical parameter or the it is at the distance d from the face of the support. So the distance is c, 26 inches. This is face of the support. This is the line of critical shear, one way shear. Now the critical section for one way shear is located at distance d from the face of the column as shown in this figure. The center of the pile closest to the column is located 19 inches inside of the critical section. See this pile, its center is 19 inches inside this critical section, which is the dotted line. The solid line is the center of these two piles, okay, which is greater than d by 2. See, d by 2 is 6 inches and this distance is 26 inches. Okay, thus the reaction from this pile is not considered. Okay, this pile is not considered. The two remaining piles are located at these two piles, number 1, number 2. These are located at, this is 26, right, minus 36 minus 11. What is 36? See, 36 is the distance, center to center distance of these piles and the center of the column, minus 11. 11 is the is half for half side of the column. So if you are deducting 11 from 36, so you are getting the distance from the face of the column to the center of the piles. Okay, so this comes out to be 1 inch. See here, you got the value, this 1 inch. So what is this 1 inch? The 1 inch is uh, your center line of the piles is 1 inch inside of the critical section, which is less than d by 2. D by 2 is 6 inches. In this case, the reaction for these piles shall be based on a linear interpolation, as we have done in the previous case. Okay, and that will be between minimum and the maximum. Okay, so the minimum case is d minus dp by 2, which is 20 inches like the previous one, and the capacity will be 0. And the maximum is d plus dp by 2, which is 32 inches, and the capacity will be full. So by performing the linear interpolation, uh, you see here in the previous case it was 20.5, right? Putting the values, and you will get vu is equal to the since there are two piles now, and capacity of each pile is 48 or demand, so total vu is 96 kips. Checking the capacity, putting the values, it turns out to be 229 kips, which is much more greater than 96 kips. So you are okay for one-way shear in all the cases. Now, two-way shear at corner pile. Now, VU is equal to pile reaction, which is equal to 114 kips. Phi VC is phi 4 lambda under root of C prime B naught D, where B naught is equal to pi into dP plus D. You know the dia of pile, which is 12 inches, and you know the D, okay, which is 26 inches. Normally for an interior circular pile. For the corner pile, we are talking about the corner pile, okay. B naught is calculated as shown in the following figure. So this is for the corner pile. You can see the uh, location or the position of the corner pile. See, now this is your corner. The distance from the center of the pile to the edge is 1 feet 3 inches, which is 15 inches in both the directions. Okay, uh, dp divided by 2 is 6 inches, and the face of the column is at 9 inches from the uh, edge of the support or edge of the pile cap. So, similarly, in this direction, this is 6 inches. Now, take this 6 inches plus this 13 inches, so 13 plus 6 is comes out to be 19 inches. So you can draw a circle of radius 19 inches. See, this is the center of the circle, and you can draw this circle like this. Okay, so see this circle it has a radius of 19 inches. However, when it reaches to the center of the pile, you have to extend it as a straight line. Similarly, this circle when reaches here at the center of the pile, center line of the pile, you have to extend it as a straight line. Okay, so what is your critical parameter? Your critical parameter is this line, the one which is highlighted. Okay, this dashed line but highlighted is your critical parameter. You have to calculate it. So other terms will remain same, however b naught will be calculated from this area. See, phi 4 into lambda. See, lambda under root of c prime, the d is same, 26, right? So the difference is in the b naught, the critical parameter. So pi by 4 multiply by 12 plus 26. You know what is 26 and what is 12. Okay, so plus okay, you have to multiply this term with the pi by 4 and plus 2 into 15, and you know what is 15, right? 6 plus 9 is 15. So putting the values in this equation gives 295 kips of 5 vc. Vu is less than 5 vc. So okay, the calculations above may be simplified using the approximation of equivalent sections as shown in ACI 31814. Obviously it's section 8 10 1 3. Okay, but let me show you what this b naught you have obtained from. For example, in this slide you saw that for the circular column b naught is equal to pi into dp plus d. However, for the corner piles, sorry, it's not column, it's pile. In this case both are different. So in this case, since you are taking just one quarter, see, one quarter of the circle, right? So it will be pi by 4 into dp plus dc. Pi by 4 into dp, dia is 12 and d is 26. So one thing, and since you are calculating b naught, so it is from here to here you have calculated it. Now you are left with this length which is 15, and you are left with this length which is 15. Okay, so 15 plus 15 plus this length which is pi by 4 into dp plus d. So what is dp? Dp is this, and what is d is this. Okay, so you have obtained this. Now coming to the one-way shear at corner pile. The one-way shear is checked at a distance d, but no more than 13 inches, okay, from the face of a corner pile as stated in the reference. The critical section occurs at a 45 angle with respect to the edges of the pile cap, and Vu is the reaction of the pile, which is 114 kips. Calculating 5 Vc by ACI equation this, where B is calculated as shown in the following figure. Now, this is for the one-way shear critical section for the corner pile. Okay, in this case, you can see that the distance from the edge of the pile cap to the uh, edge of the pile is 9 inches, and of course from the center is 1 feet and 3 inches. Now, since this is a corner pile, so we are taking it in a two directions. The two-dimensional figure, it is similar in both the directions. So now consider it that this distance is 9 inches, right? This distance is 16 inches. So you can obtain this distance, okay, from the face of the column to this point. It is simple Pythagoras theorem. So this distance, the diagonal distance, it is since the angle is 45-degree, so it is very easy for you. The distance comes out to be, the diagonal distance is 15.2 inches. We know the dia of pile, which is 12 inches, and as we saw from on previous slide that it cannot be more than 13 inches. Okay, so keep in mind that this critical parameter is can be a maximum at 13 inches. So you got this dimension, you got it. Okay, so since this is a 45-degree, and if you know one side, you can calculate other sides. So this side turns out to be 40.2 inches, and also this side is 40.2 inches. Now using the same equation, and you know the critical parameter. Okay, this is 40.2 plus 40.22 into 40.2. Putting the values in it, you get Vu is less than 5 Vc. So okay, in this case again you are greater than 114, so you are on safe side. And two-way shear at interior piles. For interior piles, if two-way shear parameters overlap, the modified critical shear parameter should be taken as that proportion of the smallest envelope of individual shear parameter that will actually resist the critical shear for group under consideration as shown in the following figure. It's as per ACI section this. Vu, as we know that for single pile is 114, and in this case we are considering two piles. So combined Vu will be equal to 228 kips, right? Now putting the values in the capacity, B naught is calculated as shown in the following figure. So the dia of the pile, you know, it is how much? 12 inches, right? So the radius will be 6 inches, and 6 inches plus this 13 inches, so 19-inch radius, as we have seen here, right? So coming, why it is 13 inches? Because here it says that it can be no more than 13 inches, so we are taking it 13 inches, right, in all the cases. So this circle, the semicircle, is of 19-inch radius, and if you extend it, to draw the critical parameter, uh, and draw for the second one as well. So they both intersects at this point, okay, and the envelope, this has been sheared by both the critical parameters. Both the piles are at 36-inch apart. Now putting the values in its equation, all other parameters are same except for this b naught, okay. So how it calculated the b naught? See, you know this thing, okay, 2 plus 30, 2 into 36, since this side, this dotted line from here to here, this is 36 inches and this is 36 inches. So you can easily calculate or simply add these two, okay. Now you are left with this semicircle and this semicircle, okay. So length of the semicircle, since there are two semicircles, so it is 2 into pi into 12 by 2 plus 26 by 2. See, the 12 is the uh, dia of pile and 26 is the dia of sorry, depth of the what you say, the footing or pile cap, okay. So for example, let me take you to this point. See, pi into dp plus d, so this is the same thing, dp plus d, so this is dp by 2 plus d by 2. Why it is 2? Because it's semicircle, okay. So it comes out to be 944 kips. Your demand was 228 kips. Okay. So the reference states critical sections for two-way shear of the edge piles overlap and are incomplete. They fall outside of the pile cap and shear requirements do not control for these piles. Okay. Now the last one in this section is pile cap overall depth requirements. Overall depth of pile cap shall be selected such that the effective depth of bottom reinforcement is at least 12 inches, okay. We already knew this thing from the statement as well. H minimum is equal to 12 inch plus cover plus embedment. So 12 plus clear cover 3 inch plus embedment 4, it comes out to be 19 inches and our depth is 26 inches. So we are good with these requirements. So 26 plus 3 plus 4, which is embedment and cover, it's 33 inches, which is much greater than H minimum. Thus, use a final pile cap thickness of 33 inches, which includes the embedment and cover requirements as well. So, third step is the pile cap flexural strength and reinforcement. In a pile cap foundation design, flexural moments are evaluated in two orthogonal directions, which is mx and my. Okay, now from now onwards, keep these two terminologies in your mind, x and y. To simplify design calculations, an average value of d is used to represent both reinforcement curtains in the x and y directions. Number one part is for affected movements in short direction. Okay, let me show you again which one is short direction. See, this 7 feet 9 inches is short direction, this 8 feet 6 inches is long direction, okay. So in the short direction, the factored moment at the critical section is obtained by multiplying the reaction from three piles by the distance from the center of the pile to the critical section or at the face of the column as follows. There are three piles, capacity of each pile or demand on each pile is 114, right? Multiply by 7.75 divided by 2 minus 1.25 minus 22 divided by 2 into 12, okay. Now you know that 22 is the uh, size of the column. You have divided it by 2 to come to the center line, okay, and you have divided by 12 to make it in feet. This is 1.25 in feet and this is 7.75 the total. Okay, let me take you to this figure again. For example here, okay, this is 7.75 feet total. When you divided by 2, you came to half, okay, the center line. You deducted this length and you deducted this 1.75. See, so this is the distance between here, the center line of these piles, to the face of the column. You are getting me? So solving this equation, you get 584.3 keeps fit in the shorter direction. Now coming to the longer direction, the factored moment at the critical section is obtained by multiplying the reactions from three piles by the distance from center of the piles to the critical section. Again the same thing, but in this case the values will be different, as you know. So 114 into, why it is 1, because the middle column has a different distance and the two columns at the edges had different distance. See, let me, yeah, here. So this column will have a different distance from center of the pile to the face of the column. However, these piles will have a different distance from center to the face of the column. So all these decisions we have already evaluated previously, so the result will be 541.5 kips fit. Required flexural reinforcement in shorter direction. You know this moment, you know the depth. To determine the area of steel, assumptions have to be made whether the section is tension or compression controlled and regarding the distance between the resultant compression and tension forces along the footing section J. Okay. In this example, tension controlled section will be assumed, so the reduction factor phi is zero point 0.9 and JD will be taken equal to 0.93 of 0.983 of D. The assumptions will be verified once the reinforcement area is finalized. So assume JD is equal to 0.983 into D, which is 25.56 inch. Putting the values, we are getting area of steel. Recalculate A. From this area of steel, you will get 0.879 inch. From this area, small a, you can calculate the depth of compression block C, or the depth of the neutral axis, 1.03 inches. Putting this in this equation of strain intense tension steel, you get value which is greater than the yield strength. Therefore, the assumption that section is tension controlled is valid and your steel is yielding. Now selecting the area, putting the values, we are getting 5.08 square inches. Checking for the minimum reinforcement requirement, the minimum reinforcement is 6.06, which is greater than our provided reinforcement, so we will provide this minimum reinforcement. Okay, maximum distance or the spacing is lesser of these two, which is 18 inches. So providing 11 number 7 bars with total area of 6.6 inches satisfies strength requirements. For rectangular foundation, a portion of the total reinforcement in the short direction shall be distributed uniformly over a band width equal to the length of short side of footing, centered on center line of columns. Remainder of reinforcement required in the short direction, which is 1 minus gamma s into total area of steel, shall be distributed uniformly outside the center band with width of footing. Okay, this requirement is also helpful to address the effects resulting from load concentration near the column, of course, and two-way behavior in foundation structures. This is a similar effect to what is required in elevated slab supported by columns, which is flat plate. The FEA results at the end of this example will demonstrate this behavior indicates where bars need to be concentrated according to reinforcement contours. So calculating that gamma S, which has formula in ACI, it comes out to be 0.95. So provide 95% of the bars in the center band, okay, and the remaining in the outer band. Thus provide 12 number 7 in the short direction. Coming to the long direction, we have this moment, we have the perform the same steps and uh, again validate the assumption. If it's okay, select the area of steel, check against the minimum reinforcement requirement and check the spacing requirements. So provide 10 number 7 in the long direction. These bars are spaced uniformly over the width of the pile cap. And the fourth step is reinforcement bar development length. Okay, so it says that flexure reinforcement must be properly developed in a concrete foundation in order for the foundation to perform as intended in accordance with the strength design method. Okay, the concept of the development length is stated as follows. Minimum length of reinforcement must be provided beyond the locations of peak stress in the reinforcement in order to fully develop the bars. The development length for the pile cap is calculated by ACI equation 25423A, okay, which is for the development length, and there are different coefficients. And for normal weight concrete, these coefficients are equal to 1. It solved this value CB plus KW divided by DB, it comes out to be 2.5. And the dia of bar is 0.875, Fy is 60,000, lambda is 1, Fc prime is 4,000, 3 by 40. So after solving the equation, you get the value of 2.7 feet. Okay, here you will get 2.1 feet, and it has explained the values. Why lambda is 1 for lightweight modification factor, its normal weight concrete it is 1. All these psi values are 1. Why these are 1 for this case, it is mentioning here. This value is equal to 2.5 because it is confinement term and shall not exceed 2.5. This is the maximum value we have used, okay, because while we solved it we got 3.4, which is greater than 2.5. However, we cannot use more than 2.5. The provided bar length is equal to, in our design what we provided was, it is shorter side, okay, because we are talking about 7.75 feet, not 8.5. So half of the pile cap dimension minus half of the column dimension minus 3 by 12, okay, the 3 inches outside the pile, so it's 2.7. It is a clear cover, okay, 3 inches, see, mm, where we have provided it for the, let me show you, see, this is the cover, 3 inches, right? So after solving it, it's 2.7 feet, which is greater than the required development value 2.1 feet. So okay, we are on safe side. Because available development length is greater in the long direction, the bars in that direction can be fully developed. Note that transfer of forces between the column and the pile cap needs to be checked to ensure interface reinforcement is provided, or the column vertical bars are adequately developed and lapped with foundation flexural reinforcement, okay. So it is up to the designer to make sure of these requirements. Now, the same analysis and design was performed using a finite element software, and the results are summarized here and compared for you to visualize it and to check the adequacy of the current results. It is the hand calculation used in this example. This is from reference from where I have taken this example, and these are results from finite element method in one way action and two-way action. In short direction you can see the area of steel required and the design moment, and in the long direction. So the result of all hand calculation and the reference used illustrated above are in close agreement with the automated results obtained from the finite element method. The difference in the design moment and required area of steel between the hand reference and FEM is primarily a result of the analysis method used and can be related to difference in two key areas. Number one is what? Design moment values, and number two is twisting moment contribution. And you can better read it from the text. Similarly, this is the difference in shear, the hand calculation, values in the reference, and finite element model. For two-way shear, check around column. Using ACI provisions, the hand reference solutions neglected the contribution of two piles near the column. If you remember, okay, that we were neglecting the columns, the piles, the two piles near the column. However, if we reflect this condition in FEM, the same results can be obtained. See, you can ignore these two piles in the FEM and you will get the same results. So two-way shear check around interior piles and two-way shear check around corner piles. For interior piles, it says that if shear perimeters overlap, the modified critical perimeter should be taken as that portion of the smallest envelope of individual shear perimeters that will actually resist the critical shear for group under consideration, right? We already discussed it. The hand and reference solutions used this provision. However, FEM reports standard shear perimeters for three conditions: interior, edge, and corner. Only considering adequate spacing and edge distance is provided to prevent overlapping or truncated shear perimeter. And in case of corner piles, for corner piles, the reference and hand calculations use the smaller of the two parameters. The reference mentioned that this approach is similar to the investigation of two-way shear in two-way slabs, where a cantilevered portion of the slab is adjacent to an edge column. Okay, FEM investigate two-way shear around the corner piles using the critical section that is located at distance d by 2 from the face of the pile. For the two-way shear check around column, FEM uses d as the effective depth used in the pile cap. For two-way shear check around the piles, FEM uses D as the thickness of the pile cap minus the pile embedment. So it takes different around the column shear check, okay, and different around the piles. This was the difference in FEM. However, I'm just representing discussing it here. You don't need to worry about FEM because in this example we didn't perform any FEM analysis. I am just presenting results for your convenience. So these some slides are just for the discussion and nothing to do with this example. Okay, your design ends here, right? Okay, thank you very much and see you in the next video. Take care.